Everyone, welcome to the Project Tier Speaker Series featuring Michèle Nuijtenm. My name is Kara Moore. I'm an assistant professor of psychology at Oklahoma State University and a Project Tier fellow. On behalf of Project Tier's co-directors, Richard Ball and Norma Medeiros, and the members of Project Tier's executive committee, I'd like to welcome you to today's session. Today's presentation is one of 9 weekly webcasts that feature leaders in transparency and reproducibility. We're really excited to offer this series and would like to thank the Alfred P. Sloan Foundation for their generous sponsorship and continued support of Project Tier. I'd also like to thank my Haverford colleague, Alex Savoth, for coordinating the technical aspects of this series. If you experience audio or video difficulties during the broadcast, please know that we will be recording today's session and posting it to the Project Tier website for later viewing. And now to the reason you're here. It's an honor to introduce today's speaker, Michèle Nuijtenm. Michèle is an assistant professor at the Meta Research Center at Tilburg University, where she studies reproducibility and replicability in psychology. She obtained her PhD in methodology and statistics at Tilburg University in 2018. Her PhD thesis, titled Research on Research, a meta-scientific study of problems and solutions in psychological science, was awarded the Tilburg University Dissertation Prize. As part of her research, Michèle co-developed the free tool StatCheck, a spell checker for statistics, which I myself have really enjoyed using. StatCheck has gained popularity as a pre-publication check. Since its launch in 2016, the web app has been visited tens of thousands of times, and the journal Psychological Science and the Journal for Experimental Social Psychology have both made StatCheck a standard element in the peer review process. Beside her research, Michèle is closely involved with the Society for the Improvement of Psychological Science, having been a member of the executive committee and past chair of the program committee. She is also part of the program committee Replication Research of the Netherlands Organization for Scientific Research, advising them on distributing funding for replication research. Michèle will present checking robustness in 4 steps for approximately 45 minutes, after which we'll have a few minutes for questions. Throughout the presentation, please type your questions in the Q&A panel on Zoom. I'll assemble those questions and pose them to Michèle as time permits at the end of her talk. So without further ado, let me turn the broadcast over to Michèle.
Thank you, Kara, for the introduction. First of all, I am really happy to be here. Well, to be here in my own house, actually, but to be virtually here in this series of lectures. I think it's a really great initiative, and the lineup of speakers is really awesome, which is why I'm even more honored to be a part of this. I really enjoyed the previous 2 talks, and I'm also really looking forward to the rest of the talks that are still coming. But today I would like to discuss with you an idea about how we can check robustness in a more efficient way, namely checking robustness in 4 steps. And before I talk about that, I would like to give you a little bit of my background. Kara already said most of this, but just so you have clear in mind that my background is psychology. Although I specialized really in meta research. So I'm part of the Meta Research Center, which means that my entire PhD was really focused on doing research about research, and specifically reproducibility and replicability in psychological science. And the reason that I think it's important to mention that explicitly is that it might give you an idea why I focus on some aspects and some type of problems instead of others. It might also explain some of the terminology I will use. I'll make sure to explain everything that I say. I do think that a lot of things that I study or talk about, even though they're focused on psychology, I think they're very relevant for different fields. Well, I'm hoping we have an interdisciplinary audience today, so if you have any questions or if you disagree completely with the way that I'm phrasing things, I would love to know. But this is pretty much where I'm coming from, just to give you a little bit of an idea. So Today, I would like to talk about assessing and improving robustness of psychological science or of science in 4 steps while using minimal resources. So it's really about efficiency and saving money, saving resources. So before we really have to dive in, we can dive into that. The first thing we need to talk about is what I mean with robustness. And I struggled a bit trying to come up with a definition, and I think it's a really tough thing to do, and you very quickly sort of dive deep into the realms of philosophy of science, and I didn't really want to get into that deeply. So what I mean when I talk about robustness is pretty much say that you're reading an article. The article states, we found an effect of X on Y, then robustness means something like, can I trust this result? Will this result hold up? Can I build on this? Can I trust it? That's sort of the intuitive interpretation of it. And for a very long time, and still, I think, the way that people would argue to assess robustness is through replication. And if I say replication, I really mean doing the study again to see what comes up a second time. So for instance, if the first study says we found an effect of X on Y, people do the study again in a replication and they do not find the effect of X on Y, then you can wonder whether a result is robust. So replication comes in different flavors. And just very broadly, I would say it's pretty much a continuum. And again, you can argue or talk about this for a very long time. This is a simplification, just to give you an idea. Replication goes pretty much from direct or exact replication all the way to conceptual replication. And with exact replication, you pretty much ask the question, do the results hold up if I do the study again? As closely to the original as possible. So try to get the same population, the same variables, same operationalizations, same everything. Whereas in a conceptual replication, you would ask more of a question, do the results hold up if I test a hypothesis, so the same hypothesis, but in a different way, which could mean maybe a different population. Maybe you want to operationalize your variables slightly differently. Maybe you want to choose a different type of setting for your study, things like that. And both kinds of replications are very important, I think, for the progress of science and to understand which findings are trustworthy. They just focus on different questions. So I would say that direct or exact replication really focuses on sort of the falsification of a specific prediction. So at a very close level, does this specific experiment replicate? Can I falsify this specific finding or not? Whereas a conceptual replication focuses more on generalization. It's like, all right, we have this idea that X has an effect on Y, but is that always the case? And with generalization, we often also think about how can we use this in practice. Now, if we're asking the question if a specific finding is robust, then I would argue that it makes sense to first focus on direct replication before you get into conceptual replication. So I would say it is most important to know first whether that specific experiment is not a fluke, whether the results will show up again and again before you start building on that. So this would be, I think, a good strategy to assess whether a result is robust, replication. The downside of replication is that there is quite a lot of time and money and effort involved, because you have to do a study again, which means finding participants again, setting up the whole study, getting research time for that. And that is not always feasible. And especially if you think about the fact that people are often not really rewarded for replications, we still have this idea that replications don't get published as often. So why would you then spend your probably rare resources on doing a replication study? And that is why I would argue, if you want to know if a result is robust, focus on reproducibility first. Now here we get into a little bit of terminology, and these terms are used differently in different fields. So I'd like to define what I mean with this. So replicability, what we just talked about, a study is successfully replicated if the same or a similar result is found in a new sample. So this is pretty much the key of replication. You really run the study again, you have new participants and see if you can find your result. Whereas reproducibility, a study is successfully reproduced if independent reanalysis of the original data using the same analytic approach leads to the same or similar results, roughly. But the key difference between these two concepts is that reproducibility is really about do the numbers hold up? So if you give me the same data and the same analysis strategy, I should be able to find the same results as in the original study. And the reason, where I think that reproducibility sort of fits into this line is pretty much here. So we have the direct replication, really focusing on, if I do this experiment again, will these results hold up? Reproducibility is sort of one step even before that, saying, are these results correct in the first place? Because if they're not, then what are we doing exactly when we're trying to replicate a study? And this is pretty much the basis, sort of the premise of this whole talk. The fact that I think we should focus on reproducibility first before we get into replication. And let me get into that in a little bit more detail, because this is an important point, I think. So I think that reproducibility is a prerequisite for replicability. So a result first needs to hold up upon reanalysis before, I would argue, you have to collect new data. Because, let me give you an example. So say we have this same study again. They say we found an effect of X on Y. And in psychology, this is often justified with null hypothesis significance testing. So we often use p-values. And we have this convention that often a p-value below 0.05 is considered statistically significant. Now say that I get the original data from the study that underlie the study. And I reanalyze the same data following the procedures that are reported in the paper. And if I do that, I find a p-value of larger than 0.05. Then this result is not reproducible. I cannot find the number that is reported in the paper based on the original data and the original analysis. Now, if a result is not reproducible, it has no clear bearing on theory or practice, because an irreproducible number is effectively meaningless. Because I have no idea where this smaller than 0.05 is coming from, because if I do the analysis again, I get a different number. So what does this smaller than 0.05 mean? Maybe it's just a typo. Maybe it was a different analysis. Maybe it's one big question mark. So this number in this paper, I don't know where it's coming from. I don't know what the cause of this inconsistency is, but I do know that this is irreproducible, and therefore I cannot interpret it. And that's why you don't need replication to find out whether this specific result is robust, because it's not. And this is kind of the key point. This specific result, this p is smaller than 0.05, has no meaning. It is not robust because it's not based on the original data and the original analysis. So based on this idea, I would like to propose a new way of assessing and improving robustness. And the first thing, and the way that I would like to do that is by introducing this 4-step robustness check. So I would say that this is sort of a recipe to follow, and the first step to take is, I think, checking the internal consistency of statistical results. The second step would be to reanalyze the data using the original analytical strategy. Third, you could check if the result is robust to alternative analytical choices. And fourth and final, you could perform a replication study in a new sample. So this recipe can be used both to assess, but also to improve robustness. And I would like to first focus on how this strategy could potentially help assessing whether a result is robust or not. And one key point also to keep in mind while we talk about this is the fact that this strategy will be much more efficient and cost less resources than immediately going to this replication. So let's first see how we can assess robustness. So the first step of this 4-step robustness check would be to check the internal consistency of the statistical results. What does that mean? If I focus on a psychology example, then very often the key findings are justified by these null hypothesis significance tests. And these are not just a p-value, they are often accompanied by test statistics and degrees of freedom. So a bit more information about this result. And what I want to check in this first step is whether these numbers that are reported in a paper sort of belong together. So it's kind of a statistical sanity check. Do these numbers at a first glance make sense? And the reason why I would focus on that is that they sometimes don't. So let me give you an example. This is a paragraph that I copied from a published paper. And to be honest, I have no idea what this experiment is about. This is purely for illustrative purposes. But if you'll read it with me. Also, as expected, when priming condition was crossed with age group and time of memory prediction, interaction effect emerged for both the photo recall prediction statistics and the learned recall prediction. And they justify the result that there is a significant interaction effect with this null hypothesis significance test. So this is an F-test, and it has degrees of freedom, and it has a test statistic, and it has a p-value. Now, I don't know how familiar you are with these type of statistics. The people who are familiar with these type of statistics might already spot something weird in this result. But the thing is, these 3 ingredients, these degrees of freedom, the test statistic, and the p-value, they should be internally consistent, which means that effectively this says 2 + 2 = 4. Except that in this case, it might sound a bit like maybe it says 2 + 2 = 5, which would not be consistent. So if I would take the degrees of freedom and the test statistic here, and I would recalculate the p-value belonging to these degrees of freedom and this test statistic would actually be 0.86. That means that somewhere in this result, something went wrong. These results are internally inconsistent. To dive a little bit deeper into this, for my research, I often made a distinction between inconsistencies and gross inconsistencies. And the difference is whether or not it would affect the statistical conclusion. So for instance, an inconsistency would be the following. I have a reported p-value of 0.21, but if I would recalculate it based on these degrees of freedom and the test statistic, the actual p-value would be 0.20. Now, this is an inconsistently reported result, but it does not really affect the statistical conclusion. If we sort of hold on to this thought that in psychology something is considered statistically significant if the p-value is smaller than 0.05. So this 0.05 is really the cutoff. Now, a gross inconsistency, on the other hand, does affect the statistical conclusion, or could affect the statistical conclusion. So that could go 2 ways. So we could have a case where the reported p-value is smaller than 0.05, but if I recalculate it, it's larger. But also the other way around. If I have a p-value reported as larger than 0.05, so it's not statistically significant, and it is significant upon recalculation. Both these cases would be a gross inconsistency. Now, this often may seem like the typical sort of nitpicking thing that methodologists might do for fun or something. And especially when I even started in this research line, it felt a bit, just not very relevant, just like details. I was like, how important can this be? Well, we found out that it turned out to be pretty relevant because we investigated a large set of papers to see how often these things happen. And before I can tell you the results, I first have to tell you a little bit about what we did to discover that, because we had a whole bunch of papers by heart. I would say 30,000. Searching these through by hand is of course impossible. So what we did is we created the R package StatCheck. StatCheck is free. It's on cron. And what it does is the following 4 steps, effectively. It's a pretty simple algorithm underlying it. So the first thing it does is you feed it an article in PDF or HTML format, and it will sort of convert it into a plain text file. Then it will search through the text to look for APA reported null hypothesis significance testing results. So these set of test statistic degrees of freedom and p-value that we just saw. Based on these extracted numbers, it will recompute the p-value. It will recompute the p-value, period. And the fourth step is it will compare the reported p-value with the p-value that it recomputed using these other numbers. Now, when we did that and we sort of released it on this set of papers, I said 30,000. In the end, in about 60% of these, we actually found statistics. So if we focus on this set of 16,000 psychology papers with statistics in them, we found the following. We found that in about half, there was at least one inconsistent p-value. And that sounds super dramatic, and the media loved that. They were a bit like, oh, 50% of psychology is absolute nonsense. That is a bit exaggerated, because often these were very small mistakes that didn't really have any influence. What may be more influential is the fact that we found that in 1 in 8 papers, so roughly 12.5%, there was at least one gross inconsistency where the reported p-value was significant, whereas the computed p-value was not, or the other way around. So this is not necessarily only sort of a theoretical problem to keep methodologists busy. It really seemed to be a widespread thing. And this is only one of the things you can check. And the nice thing about StatCheck is that you don't need raw data to detect such inconsistencies. It's enough to have the paper, and StatCheck will just crawl through it and find these results and see whether they are consistent or not. And StatCheck is not the only tool that does things like this. You also, for instance, have the GRIM test. And GRIM checks whether, and now I'm paraphrasing probably, whether reported means are consistent with the number of items and the number of participants in a certain setting. And for this, you also don't need to have the raw data. Now, there's also ways to check whether, for instance, the path coefficients in mediation models are consistent with each other. There is a paper where they scraped through papers to check whether reported confidence intervals were consistent with the published ratios. And for all these techniques and many more, you don't need raw data. So there's quite a lot of things that you can check in a paper with, as a sort of a first statistical sanity check. So to check internal consistency of statistical results. Now say that you've done this step, you've checked all these numbers in a paper, and this turns out well. There's no inconsistencies that you can find. Well, that's good news. Then I would say, then you can carry on to step 2. Now say that you find inconsistencies in a paper, then you can decide to stop. You can say, well, this result, as it stands here in this paper right here, is not robust, because I have no idea where it came from. It's impossible to get an inconsistent result if you would analyze the data and report the data correctly. So the result as reported is not robust. That's just a sort of a final conclusion. And what follows from that is that replicating, is of no use. And here people might already feel a bit uneasy because it maybe feel a bit over the top to immediately sort of like throw the whole study out of the window. But what I would say is that replicating that result, the inconsistent result, if you want to focus on falsification of your prediction, is of no use. So what you can do is either stop, but alternatively, what you could also try to do before you stop is see if you can find the cause of this inconsistency so that you can correct it. Because if you can get your hands on the raw data, for instance, and you see like, oh, this wrong p-value was just a typo. The example that I showed you in the beginning, it's very possible that that f value that was reported as 0.03 should have been 10.03. And once you fix that and the result is not inconsistent anymore, then it is suddenly a meaningful result again, which means that you can continue. So in both cases, you could decide to continue with this 4-step check. And the second step of this check would be to reanalyze the data using the original analytical strategy. So here you can see that this step is already needs a bit more effort than this first step. The first step is just a sanity check. Here you would need to get your hands on the raw data. And we've talked about this in the beginning. What does this mean? You have to get the original data, you reanalyze these data following the reported procedures, and you check whether the results that roll out of that are consistent with the ones that are reported in the paper. This may sound relatively straightforward. In practice, it's almost never straightforward. So there's kind of a lot of things that can go wrong here. The first thing is getting the data. And I don't know how this is in other fields. Well, I do have some sense how it is in other fields, but in psychology, at least, data are often not available. There is a lot of work on that, and it's getting a little bit better, but still getting your hands on the raw data is not a given. But say that you do, say that people do share their data, then often these data are unusable or the analytical procedure is unclear. So for instance, you could get data without variable names. So I don't know if you guys have any experience with SPSS files, but by default, all variables are called var 0001, var 0002. And sometimes people forget to change these into meaningful variable names. Now, if you get these data as someone who wants to reanalyze this, then you can imagine that it's really hard to do so. Even if the data are perfectly clear, it might not always be clear what exact analytical procedure has been followed, because maybe the paper just says we did an ANOVA. What kind of ANOVA did you do? And which exact data did you include in that? And did you remove any outliers? And there's just a ton of things that you can vary, even if you think you're doing something very simple as just an ANOVA. So the analytical procedure is always, is not always clear. But even if you have the raw data that is usable and you have the analytical procedure, it could be the case that results are not reproducible. And there's also data that this is often the case. I will not sort of try, I was gonna sort of like throw numbers at you of the prevalence of these reporting errors, but these numbers I would sort of have to tell you by heart, and I will definitely make a mistake, so I won't do that. But I can tell you that this is not, again, a theoretical problem. Results that are reported in papers are often not reproducible. And if they are, then that's great news. Then you have sort of successfully finished this step and you can continue with the next step. But if you did not successfully complete this step, so if you cannot get your hands on the raw data, or if the analytical procedure is unclear, or if you just got a different result out of reanalyzing, then pretty much the same story holds as in failing step one. So at that point, I would argue the result is not robust in the sense that you cannot verify where that number came from. And it may seem a bit harsh if it's the case that the data were not available to conclude that the result is not robust. That would be sort of the hardcore attitude, I would say. But the thing I think we all can agree on is if you do have the data and you reanalyze it and you get a different result, that replicating it, or that at least that result is not robust, and that trying to replicate that specific result is not really of any use. Because think about it, you have a result reported in the paper, you reanalyze it, you get a different result, then what result are you exactly trying to replicate here? So here I would again say you can stop here and conclude, well, if my question was, is this result robust? Then the answer is no, it is not. However, if you want, you could, if you want to sort of continue through this 4-step plan, you could also see if you can find the cause of the inconsistency and correct it. So pretty much the same as in step 1. And this can be, for instance, by contacting the original author, seeing if you can figure out what went wrong. Maybe it's obvious that it was a typo. And if you can correct it, then you know again where the result comes from. It has meaning again, and then you can continue with the next step. And this next step is to check whether the result is robust to alternative analytical choices. And if I sort of give you an example, say that we have the original data, we reanalyze following reported procedures, and we get the same result. We get this p is smaller than 0.05. However, how robust is this result? What if we have chosen a slightly different path in the analysis? And you may or may not know, but in many statistical analyses, there's a ton of analytical choices you have to make that are often quite arbitrary. So yeah, maybe if I reanalyze the original data, but I include that one outlier that was removed in the original procedure, and then I find that my result is suddenly not significant anymore. Or if I remove one seemingly arbitrary covariate, then maybe my result is not significant anymore. Maybe if I exclude the last observation that was recorded in my data set, then the data suddenly, the analysis is maybe not significant anymore. Maybe if I would test two-tailed instead of one-tailed, etc., etc. So there's a ton of choices, and if it turns out that only one specific path leads to this p is smaller than 0.05, and pretty much everything else that you can come up with that is reasonable to do does not, then you can wonder how robust this result is. And the reason that this is an important step is that there is quite some data out there that this sort of flexible use of these analytical choices, and maybe even opportunistic use, whether it's conscious or not, is quite widespread. So there is this is once called the Garden of Forking Paths by Andrew Gellman, and there has been quite some data that psychologists at least engage in this, and I think that probably holds for many people who use statistics. And this step is slightly different than the other steps we discussed. So if we go back to this sort of line from reproducibility to exact replication to conceptual replication, step 1 and step 2 are like all the way sort of at the far left. So here I would really say, if you fail this step, then the result is not robust and it does not make sense to replicate it. Step 3, checking whether it is robust to alternative analytical choices, is somewhere in between checking just whether the numbers are correct and doing an exact replication. It's sort of seeing like how steady is this result? Would I see it again if I change like small things in my analysis? So here, if you fail this step, I would not immediately say, well, the result is not robust, it doesn't make sense to replicate it. What I would say here is, well, stop and think. How easy was it to break this result? And if it was a completely arbitrary change in the analysis, and any arbitrary change could change the result, could break it, how likely is it then that this result will replicate in a new sample? So if it's already not robust to a tiny change in the statistical analysis, imagine what would happen if you would have a completely new group of people trying, and with them trying to replicate the same result. So here, you might want to think twice before you invest your resources in performing a replication study. However, if it turns out that that the result is robust to alternative analytical choices, then I would say go ahead and perform a replication study in a new sample if you want to answer the question, is this result robust or not? And the nice thing about first having followed these 3 previous steps, or another nice thing I would say, is that if you then perform the replication study and it fails, so you find a different result in your replication study than in the original study, this failed replication is more likely now to have bearing on the effect. If you haven't done these steps before this, and you have a failed replication study in your hands, then it could be that a replication could fail for a ton of reasons, but a possible reason could also be that the result that you tried to replicate was just a typo and it doesn't mean anything. And now you can sort of rule out that alternative explanation for a failed replication. So that is how I think that this strategy, this 4-step robustness check, can help in more efficiently assessing whether a result is robust. So by using fewer resources and more quickly having an answer to the question, is this robust or not? Now, I think that this strategy, this 4-step plan, can also be of use when you want to improve robustness. And I will just go through these 4 steps again and sort of, giving some ideas how I think we can, as researchers, improve the robustness of our work, or at least facilitate the checks that people can do on our work. So the first thing is checking the internal consistency of your own statistical results. And that you can do, for instance, with StatCheck. So StatCheck is, as I said, an R package, but for people who are not familiar with R, or people who just don't want to install things in R, which often holds for me if I want to check something quickly, we created a web app at statcheck.io, and you just have to sort of click a button, upload a paper, and it will give you back a table of the results that it found and whether they were consistent or not. And just one small remark there, that StatCheck is specifically designed for APA reported results, and it doesn't find results reported in a different style. So if it doesn't find anything, that might be a reason. StatCheck is actually now used in the peer review process of psychological science and the Journal of Experimental and Social Psychology. And I think it's a useful way of making sure that you don't have effectively statistical typos in your work. So you can compare it to a spell checker, I think, a spell checker for statistics. And there's a ton of other things that you can check just by going through your numbers and making sure that you didn't have any consistency errors. So this is just one of many examples. A second thing you can do as a researcher to improve the robustness of your own work is to facilitate reanalysis of the data. And I think you can do that in several ways that require more or less effort. So the first thing I think, we should all do, with some exceptions there, but the default I think should be to share data. Without data, we can never check whether, we cannot check whether results make sense or not. And if we do check them with these internal consistency checks, we can never find out why something was inconsistent. So without the data, we won't get very far. However, if you want to put in a slightly more effort, share well-documented data. So make sure that you don't only share your spreadsheet, but also create a code book that explains which variables are what. One sort of step on top of that is to also share analysis scripts. So describing your analysis in your paper is often, does often not have a lot of detail, which makes sense. You don't want to, in a paper, you also want to engage the reader. You want to make sure that they don't get lost in like a bunch of numbers and symbols and everything. But if you share your analysis script as supplemental material, then that is the most transparent way, I would say, to really say what you have done in your analysis. If you want to make sure that your analysis script is correct and readable, you could decide to have sort of in-house code review. So you don't only share your analysis script. Before you share it, you ask your co-authors pretty much to take the role as co-pilot, to go through your script and make sure that everything runs, that they understand what's going on. One step even further would be to have this code review as a part of the official peer review process. And if you want to sort of go full out, then I think we've had experts talking on this. Victoria probably knows a lot more about this than I do, and we might have some people coming up in the rest of this lecture series that can tell you all about this. So ask them how to do this, but create sort of a fully reproducible literate programming document, dynamic programming, so that you have blocks of text intertwined with actual code that automatically sort of fill out your statistical results in your paper for you. For instance, with our Markdown, putting it on CodeOcean or Docker to make sure that all the packages you use and the software is completely the same version and everything. So there's a lot of things you can do to facilitate reanalysis of the data. If you have never done that before, I would sort of suggest to start slow and sort of take baby steps up. The third thing you can do to improve the robustness of your own results is report whether your result is robust to alternative analytical choices. And sort of a mini version of that would be, for instance, I think the 21-word solution, as it's called, by Simmons and colleagues. And they suggest that you include a sentence in your paper where you say that we report how we determined our sample size, all data exclusions, if any, all manipulations, and all measures in the study. And this sort of holds you accountable for the choices that you make, to make sure that people don't think that you maybe have chosen the best analytical path to show the result that you wanted to show. A slightly more sophisticated way, or a more detailed way to report whether your result is robust to alternative analytical choices could be, for instance, just sensitivity analyses. And this may sound like really ridiculous to people who are not from psychology. I think that in economics, for instance, it's quite normal to do sensitivity analyses. Correct me if I'm wrong. In psychology, this is not very common. So you could require sensitivity analyses, or sort of a form of that, a multiverse analysis, and you can look up what that is. I highly recommend reading that paper. But effectively, what you would do is then go through all these different paths yourself, do all these different combinations of analytical steps, and then report that entire process in your paper or in supplemental materials if you want. But yeah, having done the work for the other readers. And finally, facilitating replication in a new sample. We haven't talked a lot about replication in itself, mainly because I wanted to make the point, maybe we should first focus on reproducibility first. But if you are working on creating or improving the robustness of your own work, make sure that you facilitate replication in a new sample. And what do I mean with that? Let me give you an example. This is a tweet that was sent out by Fiona Fidler at the Meta Science Conference in Stanford last September. She tweeted, Tim Arrington wins most depressing slide of Meta Science 2019 so far, which is a dubious prize. But Tim was presenting some of the preliminary results from the reproducibility project Cancer Biology. And there the word reproducibility is used as how I use replication. So they try to replicate a lot of studies in cancer biology. And the question on his slide is, for how many papers or experiments could we design a full protocol based on the paper and no input from the original authors? And I sort of blocked out the results. So take a moment and make a guess in your mind. How many experiments do you think this holds for? And I'll show you. And if for the people who said 0, you have 1. So 0 of 51 papers had enough information in them to facilitate, to allow for a good protocol and to do a real replication of what happened, because it was just unclear what happened. So this advice is maybe a bit of an open door, but apparently it's not. Write detailed method sections, and if you don't have space for that in the journal where you want to publish, put everything in an appendix, put it online somewhere, share your materials, and share your protocols. All right, so just a little bit of closing thoughts before I wrap this up and open the floor for questions. The whole sort of idea of this talk was that with this 4-step robustness check, I would argue that it's more efficient to both assess and improve robustness. Now, there's a couple of things to keep in mind when talking about that. This is relevant if you're interested in the robustness of a specific study. This is not necessarily relevant if you want to know whether a certain theory holds up. Like it's not the case that you are not allowed to do any replications anymore of any sort of form, to do any conceptual replications of a study just because one number didn't turn out the way it should have been. Similarly, I think context matters. So an inconsistency somewhere in the 3rd decimal of a result that is somewhere in a footnote after the references is a different story than not being able to reproduce the key finding of a certain paper. So this is not sort of an automated path, like once you find a mistake somewhere in an analysis, just toss the paper out. That is not necessarily what I'm trying to say. Even if you absolutely disagree with this idea that you have this sort of hierarchy or this incremental set of steps that you should follow, I think the one thing we could definitely agree on is that regardless of this logic of the 4-step robustness check, all published research should always be reproducible. And with that, I would like to already thank you for your attention. Yeah, I think I would be happy to take any questions you may have. So I think I'm giving the floor to Kara.
Thank you, Michèle, for a really interesting talk. And I think one of my first questions that I had as you were going through the 4 steps initially was, how do we then apply this to our own work? So I'm so glad that the second part of your talk was really about that. So we have questions that have come in while you were speaking, but those of you, if you have questions now would be a great time to send them in. So I'll start with just the first question that we have here, which is, what should someone do if they find an inconsistency in their work, but can't figure out how it's inconsistent?
Oh, well, first of all, that would not be a nice situation to be in, I guess. So I think if I understand the question correctly, is like you figure out that there's something wrong, but you don't know why it is wrong. So you don't know where the inconsistency came from, I guess. I think in such a case, you would have to reanalyze your data, I would say, because if you have a set of numbers in your paper and you don't know, and they don't match up and you don't know where it came from, then it's really hard to trust that result, because it may be that just one of them, so if I take the example of having a test statistic, degrees of freedom, and a p-value, if you figure out that there is an error somewhere in there, but you don't know which of the 3 numbers is wrong, then it's pretty much impossible to correct it. It's also really hard to interpret that result then. So I think in all cases, you would always have to figure out where it came from, probably by reanalyzing your data, which is another reason to share or to make sure that your scripts are well documented, so that also for yourself, it becomes easier to walk through them and find your mistake again. I hope that answers your question. I'm not entirely sure.
Thank you. Yeah, and the person who asked the question, if you have follow-ups, feel free to send those in. Another question that we have is, of the 1 in 8 papers that StatCheck have found to have gross inconsistencies, were most of these results false positives? So that is where most of the original results reported as significant, but subsequently found to be insignificant by StatCheck.
Yeah, so that's a really good question. The short answer is yes. We found a systematic bias towards reporting results as if they are significant, whereas they are not. So we analyzed it in a slightly more complicated way. If you're interested in that, the reference to the paper is at the final slide of this presentation. I think these slides will be shared as well. But we did find a significant, we did find a systematic bias towards making things seem more positive than they really are.
Thank you. One question as well is, so we have these ideas about checking robustness. Do you have an idea of who, so you talked about checking robustness for your own work, but do you have an idea for work that's already published or work that continues to be published, who should really be in charge of checking that robustness?
Yeah, that's a really, really good question. Again, I'm getting a message in my screen that I have an unstable internet connection. I'm happy that this is happening at the end of the presentation. So I apologize in advance if something goes wrong, but I'll try to answer this question. And I got so distracted. Who's responsible for this? I think, and this is maybe a bit of the lame answer. We are all responsible for this. If I make it a little bit more concrete, I would say that if you are interested in building on someone's work, then I think you just save yourself a lot of time and effort if you would first check whether you can reproduce the numbers in the work that you're trying to replicate. So say that you're just very interested in a certain theory that was coined by someone, and you cannot figure out where their numbers came from. So there seem to be statistical errors in the paper that make it hard to interpret the results. In such a case, I would say that it's not necessarily, and in many cases, maybe you cannot reach the authors anymore, so it's not possible to correct these mistakes. So you just sort of signified for yourself, well, this paper is not robust. I think that will give you a lot of freedom to then maybe design a study based on that original study, but you don't have to sort of hold so closely to the methodological steps that were reported in the original study, because yeah, this direct replication, I would argue, makes no sense to do. So you can just sort of roll with your own idea rather than trying to replicate something with numbers that don't make sense. So yeah, who's responsible for it? We have way too much literature out there to sort of systematically go through it until we have automated tools to do so. And I wonder if we ever will get there, so sophisticated. But yeah, for now, I think the most logical choice would be the authors who want to follow up unpublished work, to make that a first step in their process.
Great, thank you. Are there any plans to develop a version of StatCheck that can run on papers that aren't in APA format?
Yeah, I have so many, I wouldn't call them plans, I would call them wishes or something. There are some things I would love to do. The only problem is, or the reason why StatCheck is focused on APA is that APA style really very specifically prescribes how these statistics need to be reported. So it's always in the same order. It's always with the same, I just can tell StatCheck, just look for this letter, look for parentheses, look for a number, followed by a comma, followed by this, which makes it really easy to, or really easy, relatively easy to scrape papers and find these statistics. In pretty much every other discipline I've looked at, there is not only not APA style, but there is no reporting style for statistics, nothing systematic. So if you're listening and you think, hey, my field does have systematic reporting style for statistics, please let me know. I would be very happy to hear, but very often in several fields, there is just no statistics mentioned. It's just a p-value. And if you only have a p-value, you cannot check whether it's consistent with anything.
Okay. So kind of a follow-up to that, we have maybe kind of defining some kind of generic scheme of tags to go into the paper, like N, p-value, degrees of freedom, that StatCheck could potentially check for. And then authors then maybe would be responsible for making their papers checkable in the StatCheck format.
Yeah, that is the dream. So I think there's there's some developments in making papers more machine readable. So there are some publishers who publish in an XML format. I've never worked with that, but from what I understand, you can sort of give labels to pieces of text, which makes it easier for a machine to find out what is in which section, which is not only useful if you want to check the consistency of statistics, but also if you want to scrape anything else, yeah, for meta science purposes or any other related questions. So that would be a really great idea. For now, I'm already really happy that there's 2 journals in psychology who are just systematically using StatCheck as sort of a spell checker, because it's, yeah, to me, it seems like such low-hanging fruit. It's just, you know, it takes 0 time to run a paper through StatCheck. You might figure out some errors that you otherwise would have published, and publishing an inconsistent result is no fun for anybody. So for now, I'm quite happy with that, but I would love to see this go one step further.
Great, thank you. So it seems like these types of input errors are perhaps mistakes that lots of people could make, as even evidenced by the research that you've done with StatCheck. So besides, you know, double, triple checking your work, are there any tools out there for kind of circumventing the potential for human error and inputting your statistics in your published papers?
Yes, absolutely. I mean, the need for StatCheck mainly arises because there is human error. So I'm also, I'm totally guilty of that. I like working in Word. I know that is horribly old-fashioned, but I like to work in a what you see is what you get text editor, which means that I very often by hand copy my results in my paper. And even though I'm so focused on these statistical things, I can tell you that in my dissertation that was about StatCheck, In the end, after, of course, I printed 100 copies, I found that there were 3 StatCheck errors in my own dissertation, talking about irony. So there's definitely potential for tools that help you avoid these mistakes altogether. So one of the examples I already mentioned was R Markdown, which is a way to interleave just text from just text, human text. There's a term for it, but I forgot. With blocks of code that automatically fill in the numbers that are directly related to your data, which also mean that if you, for instance, suddenly realize that you had to remove an outlier from your data, that your numbers in your paper are automatically updated. Our Markdown can be complicated. It can be, well, it's not extremely complicated, but it has a bit of a learning curve, especially if you're not familiar with R. So there are other tools out there, I think, that help you with doing that. I don't know of many of them. I do know that one of my colleagues, Willem Slegers, is creating a tool called TidyStats, which also provides sort of a plugin for Microsoft Word, where you can sort of click on which results you want to import. And once you do that, is imported in APA style in your paper, and also with a direct link to your data. So if anything changes there, then it will automatically update. So there's definitely tools out there that prevent that human error.
That's awesome. Thank you. So I think that concludes the Q&A period for the talk. So thank you again so much, Michèle, and thank you all for being here.
Yeah, this was an absolute pleasure. Thank you all for your interesting questions. And if anything else springs to mind, and my email address is here on the bottom slide, I'd love to hear from you.